All right, so good morning, everyone. Today we will study about a series of functions. Right. So before we start, I want to recall a little bit about the series of numbers because it will help us understand series of functions much better, right? So recall the dictum that we learn previously, that I told you that a series of numbers is a kind of number, right? So is a number, right? So how did this happen, right? So we have a series, the summation from 1 to infinity of xn. So whenever we have a series of functions, whenever we have a series of numbers, we form a partial sum, right? We form Sn to be the summation from one to n of xj, right? So this is a sequence. If you let n goes from 1 to infinity, this is a sequence of partial sums. And then you take the limit. Right? You take the limit, so you get a number, right? So you get a number, and the limit of n goes to infinity of Sn. Right? The limit of a sequence. This is important. So this process, you starting from a series, you form a sequence, and then you take the limit, you get a number. It may be a non-existent number, like in the case the limit doesn't exist, right? All right, so with this process in mind, then you can replace each number xn, right, by a function. So if you replace each number xn by a function, say fn of x, right, then you can do a similar process. You form a sequence of partial sums, right? You form a sequence of partial sums, Sn, but now Sn, the partial sum, will be a function, right? The sequence of partial sum will be a sequence of functions. Right, and then you form a limit. Now the limit will be the limit of a sequence of functions, right? Right. So all right. So now you have a similar process. You have a series of functions, right? uh, starting with a formal series, right? Starting with a formal series, you form a sequence of partial sums, right? And then you take the limit, you get a function, right? Note that in the case of in the case that the limit doesn't exist, then you have a kind of non-existent function. So you do a similar process, right? So this is one thing that I want to recall, that and so that you get a big picture. This is the big picture, so that you get the definition. All right, and so that's the first thing about the process. Now I want to draw a picture, right? So that you can imagine things more clearly, right? So the first picture I want to draw is the limit of a sequence of numbers, right? So you draw a real line, right? This is the line of real numbers. Suppose you have a sequence of numbers, right? Suppose you have a sequence of numbers, say x1, right? x2, x3, and so on, right? Uh, uh, x100, right? So suppose there's a point here, x100, and then x101, right? And all the points will go to this red point, say x1000 here. So this red point, I say the L. Right? So this is a picture of a sequence that goes to L. Right? The limit of Sn goes to infinity equals L. Right? This is the picture of the limit of a sequence of numbers. Right? So before giving you a rigorous definition, I want to draw a picture so that you can see the picture first, and then when you see the picture already, then the definition will make more sense for you, right? So now I want to draw the second picture, which is the picture of the limit of a sequence of functions, right? So the next picture will be the limit of a sequence of functions. Right. All right. So I want to draw two pictures. Right. The first picture will be easy, and the second picture will not difficult, but uh, actually the two pictures will be easy. Right. So two easy pictures first. So when this is a picture that you can keep in mind when you study the series of functions, right? So suppose this is 0, right, and this is 1. All right, so suppose you have a sequence of functions, say fn, all right, x But the functions are parameterized or are indexed by the indices n, right? Suppose these functions are constant functions, right? 1 minus 1 over n. So how do the graphs of the functions fn of x look like? Does anyone know? Can you draw the graph of the function fn? What is the graph of fn of x?
Line from the OX to line E equal to 1.
Right. So I think you understand it, but the graph of fn is a horizontal line, right? So
Yeah.
for example, f1 will be 0, right? This is f1. I'll draw f1 first. Right. This is f1 of x. f2 of x will be 1/2, right? This is the graph of f2 of x. f3 will be 1 minus 1/3 will be 2/3, right? Will be 2/3. So 2/3 is here, right? So f3. But when you let the index when you let the index n goes to infinity, right? So the horizontal lines will approach the red line here, right? The green line will approach the red line. So you can see from this picture that uh, the green graphs approach the red graph, right? So this is the picture of a sequence of functions which has a limit, right? So this is the first picture that I want you to keep it in mind when you study a series of functions. Right. I want to give you the intuition first before giving you the rigorous definition. Right. So all right. So the second picture that I want to give you is the following. Right. So all right. So this is x. This is y. Right. So the second picture I want to give you is this sequence of functions fn of x equals 1 minus 1 over n of x. Right. So this is no longer a constant function. Right. So how does the graph of fn of x look like? Uh, can anyone imagine?
It will be a line cross the O center.
Right, that's correct. All right. And can you see whether can you see the limit of this sequence of functions of these
Yes.
functions? Yes.
When n to infinity, the function fn of x will close to the line E equal to x.
Right. That's correct. Very good. All right, so now I'll draw the green line first. When n is equals 1, then this is f1 of x, right? F1 of x, right? F2 of x will be F2 of x will be x over 2, right? Y equals x over 2. So let me draw it. So how do I draw it now? So let me draw the red line first. So I'll draw the functions fx equals x first. Right? So so f2 of x will be like this. This is f2 of x will be x over 2, right? F3 of x will be f3 of x will be 2/3 of x. Right? F3 of x will be 2/3 of x. Right? So you can see that as when n goes to infinity, the green graphs will be closer and closer to the red graph, right? So this is the picture of a sequence of functions approaching a function. So in this case, using the picture, you can guess, but you have to prove rigorously that the limit as n goes to infinity of 1 minus 1 over n of x will be equal to x. Right? So you say that the limit as n goes to infinity of fn of x will be equal to fx, where fx equals x. Right? So starting from a sequence of functions, you take the limit, you get a function, right? But I want to illustrate a closure point of this picture, right? So if you take an arbitrary x, say x equals 10 here, right? X equals 10 here, right? Then you see this is f2 of 10, f3 of 10, and then say f4, f5 of 10, right? So f2 of 10, f3 of 10, right? And here at the point on the function on the graph fx equals x, you have f of 10, right? Equals 10, right? So you see that the points, the pink points, right? When x equals 10, the pink points will go to the blue points, right? The blue point. So here you see that when the sequence of functions approach a function, you have a sequence of numbers at any point x, right? You have a sequence of numbers, right? Approaching a number, right? But you don't have just a sequence of numbers. You have many sequences of numbers, right? So for example, when I draw x equals 10 here, but you can take say x equals 15, right? X equals 15. You have another sequence of numbers, right? You have another sequence of numbers, and they also approach another number, right? They also approach another number, right? So you have many sequences of numbers, right? So this is the relation between a sequence of numbers and a sequence of functions. So you have upshot the upshot is that you have two pictures. Yeah, the first picture is a sequence of numbers which converge, and the second picture is a sequence of functions which converge, right? And you have the picture of a limit of a sequence of numbers and a limit of a sequence of functions, right? So I want you to keep these pictures in mind, right? So right. So one thing that I want to mention is you think in pictures, right? About sequences of numbers and sequences of functions. Right. So this is the first thing, right? That I want to tell you. Right. So the second thing, right? So the second thing is I want to come back to the dictum, right? A sequence of functions, right? I'm sorry, a sequence or a series, not a sequence. A series of functions is a function, right? Is a function. So you have a series of functions, you form a sequence of partial sums, and you take the limit, so you get a function, right? But in the second dictum, uh, it has two expressions. So the second expression is many functions can be expressed as a series of functions. All right. So to be more precise, I want to change this to a function. Right? A function can often be expressed as a series of functions. Right? It has the same meaning, but this is more explicitly. Right? A function can often be expressed as a series of functions. So this is the reason why a series is useful. Right. You have a question? Any question? All right. So I gave you the big picture. I gave you the pictures to think in pictures already. So let me start. With the definition. Right. So all right. So let me start with the definition. Right. So let me start with the definition of a series of functions. So suppose you have a sequence of functions. So you have a sequence of functions fn of x, right? So you form a formal sum. You want to you know how to add two functions, right? But now you want to add infinitely many functions, right? So you want to add infinitely many functions. You take the sum of n going from 1 to infinity of fn of x, right? So this is a formal sum, right? So this is a formal sum. Right? So infinite addition of functions. Right? This is what you want to do. You want to add infinitely many functions. So you form a partial sum, right? A sequence of partial sum. Sn of x will be the sum from 1 to n of fj of x. Right? So you add the first n functions, right? And you get a function. And from these functions, you form a sequence of functions, right? This is a sequence of partial sums. And this is a sequence of functions, no longer a sequence of numbers, right? This is a sequence of functions. And then you take the limit, you take the limit as n going to from going to infinity of Sn of x. Right? If this limit is this, right? If this limit is this, then you say that the series of functions converge, right? So if this limit is this as a function, you say that the series fn of x uh, is said to be convergent, right? So otherwise, right, you say that the series is divergent, right? All right, so let me mention about the domain of convergence, right? The domain of convergence. So 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 you have a series, the summation of the sum of fn of x. So for each value of x, so that this series converge, uh, then uh, then you uh, then you say that the series converge at this value of x, And then you take the set of all the values of x so that the series converge, right? The set of values of x for which the series fn of x, the sum of fn of x, converge is called the domain of convergence. Right, so this is called the domain of convergence. So I want to start with I want to give you two examples. Right? So let's start with two examples. The first example is let us find the domain of convergence of, say, you have a series of functions, the summation of n to the x. All right. So you see that this is a series of function fn of x, right? Here fn of x is n to the x. All right, so let's think a little bit, all right? So for each value of x, right, you want to see whether the series, the sum of n to the x, you want to see whether the sum of n to the x converge. All right, so all right, so we know that this is a series, and this is the Euler series or the P series, right? That we know before, right? So we know when it converge, and we know when it diverge, right? So can anyone tell me when it converge and when it diverge?
It convert when x less than -1 and divert when x greater than or equal to -1.
Yes. It converge when x is less than -1 and diverge when x is at least -1, right? Very good. So now you can conclude that the domain of convergence of this series of functions is x less than -1, right? Or you can say the interval from negative infinity to negative 1. Right? So I told you before that a series of functions is a function. Right? So this summation is a function, but it is only defined in the domain of convergence. Right? So has the domain of convergence, right? Right. So you can say that this series of functions is defined on the interval from negative infinity to negative 1, right? So the domain of convergence is the what is the domain of the function, right? Is the domain on which the function is defined. All right, so this is our first example, and we'll have the second example. All right, I wrote example 1, so now example 2. So you will find the domain of convergence of a series of functions, right? But now we have a series of functions x to the n, right? Instead of n to the x, now you have x to the n, right? So this is a series, the sum of fn of x, right? When fn of x is x to the n. All right, so when you have a series of functions, x is a variable, right? X is a variable. Right. But you can substitute x for an arbitrary number, right? So you can let x to be an arbitrary number, right? So when x is a number, you take the summation of x to the n, of n going from 1 to infinity, right? So this is a geometric series, right? You learned it in the first lecture. This is a geometric series, and you know when it converges, when it diverges, right? So does anyone know when it converges and when it diverges?
It converges when the absolute value of x is less than 1.
Yes. And when?
It diverges when the absolute value of x is greater or equal than 1.
That's very good. The geometric series converge when x has precisely when x has absolute value smaller than 1, right? So This is a series of numbers, but then now you change x to be a variable again, right? So this geometric series, the summation of the sum of x to the n, right, has the domain of convergence you can say the absolute value of x smaller than 1, but you can take the interval from -1 to 1, right? And it is defined, right? Defined for x from -1 to 1, right? All right, so you can use you can use what you know about the geometric series to find the domain of convergence, right? So so more generally, to find the domain of convergence of a series of functions, so normally you have to use a lot of criteria, uh, uh, for criteria of convergence of a series of numbers, right? All right, so another example that I want to give you of a series of functions is the example of a power series, right? So this is another example of a series of functions. So suppose you have an infinite sum of an times x to the n, right? So an is a number, right? Say a real number or a complex number, but here we just consider real numbers, right? Later on, when you learn higher mathematics, you can replace an by a complex number. Right? So this series of functions is called a power series. Right? This is called a power series. And later we will learn about the domain of convergence of this power series. Right? So now I'll just tell you that the domain of convergence of a power series is always an interval. Right? But this is a theorem, and I will come back to this theorem in the next lecture. But I just want to give you the example of a series of functions here. All right, so so far so good. Any questions? All right, so I want to tell you a concept which is very very useful in calculus or in analysis, right? Which is uniform convergence, right? But I want to tell you upfront that this concept is the concept of uniform convergence, right, is very useful, right? It will be used again and again, right? It's very useful. But it is hard to digest or to grasp uh, when you start. So I just want to give you a warning that this is a difficult part. All right. So it is actually not too difficult if you know how to think about it. But normally when people teach about this concept, they just give the definition and then they give the theorem. But that is why it is difficult to grasp, right? I want to teach this concept in a slightly different way, and this way, the way that I will introduce you how to understand this concept is it is not written in a normal textbook because this is I just create this way of telling you about uniform convergence so that I hope it will be more easy to understand. I hope it will be easier to understand. All right, so I want to introduce a concept, right? I want to introduce a concept which is called the rate of convergence, right? All right, so what is this rate of convergence? I can teach the concept of uniform convergence quickly by just giving you the definitions, but I find that this is not a good way of doing of teaching this concept. So I choose a slower way. Right? I choose a slower way. So all right. So now let us come back to a sequence of numbers, right? So let us come back to sequences of numbers, right? So this is not a definition. I just give you first the idea, right? So so let us do let us consider two sequences of numbers, right? So you have two sequences. Which converge, right? So take the first sequence is 1 minus 1 over n, right? And the second sequence is 1 minus 1 over n squared, all right? So these two sequences converge, and they both converge to 1. Right? 1 minus 1 over n approach 1, and 1 minus 1 over n squared approach 1. Right? However, one sequence approaches 1 much faster than another sequence. Right? So we want to measure the rate of convergence. Right? So remember that in the definition of the limit, right, you have this definition that for every epsilon greater than 0, right, there exists an n depending on epsilon, right? So that many students, when you see this definition, you are scared of this definition. But in mathematics, you have to learn not to be scared of this definition, right? You have to get used to working with this definition, right? So that if n greater than n, right, small n greater than capital N, right, then xn minus 1, right, is less than epsilon, right, or yn minus 1 or right, xn minus 1 is less than epsilon, right. All right, so how to think about this definition, right? So when right, for example, right, when epsilon is 1 over 1000, right? So 10 to the negative 3, right? Or I'll take a much smaller number, 10 to the negative 6, right? 10 to the negative 6, right? So we want xn minus 1 is less than 10 to the negative 6, right? So we want xn is 1 minus 1 over n, right? So 1 minus 1 over n minus 1 is less than 10 to the negative 6, right? So what can you tell it about the condition on n?
We can choose the n of epsilon here is 10 power 6 plus 1.
Very good, very good. That's the correct answer, right? So this implies that 1 over n is less than negative 6, right? So you have n is greater than 10 to the 6. Right? So you can see that you can choose capital N of epsilon to be 10 to the negative 6, right? So suppose you want an accuracy of 10 to the negative 6. So this epsilon measure the accuracy, right? accuracy. Then you have to go to the term 1 million in to the term 1 million in the sequence, so that these numbers will be close to 1, right, within this accuracy, right? So you have to go very far in the sequence of x to the n of xn, right? But now with the same accuracy, right? With the same accuracy, you want to consider the sequence yn, right? Suppose we want yn minus 1 to be less than 10 to the negative 6, right? But before we have xn is 1 minus 1 over n, yn is 1 minus 1 over n squared, right? So so you do the same thing. You have 1 minus 1 over n squared minus 1 less than 10 to the negative 6, right? So so now what can you tell it? What can you tell about what can you tell about n? Does anyone know?
And be greater than 10 to 30.
Yes, that's correct. So now 1 over n squared is less than 10 to the negative 6. Now you can say that n is bigger than 10 to the 3, which is 1000, right? Which is 1000, right? So you can choose n to the epsilon is 10,000, right? So we have two sequences, right? So with xn equals 1 minus 1 over n, right? And to approach 1, right? Within the accuracy 10 to the negative 6, right? You we have to go. We have to go to very far in the sequence. We have to go to x to the 10 to the negative 6 plus 1, right? X to the 10 to the 6 plus 2, x to the 10 to the 6 plus 3, and so on, right? But with yn equals 1 minus n squared, right? So to approach 1 within the accuracy of 10 to the negative 6, we have to go to only y to the 1000 and 1, right? Y 1002, y 1003, right? So you can see that the sequence yn, right, approach the limit 1 much faster than the sequence xn, right? So you can say that the sequence 1 minus n squared, right? And the sequence 1 minus 1 over n have the same limit, but one sequence approach 1 much faster than the sequence 1 minus 1 over n, right? So this is what I mean by the rate of convergence. You get it? So one sequence approached the limit faster than another sequence, right? So within the same accuracy, right? In the sequence xn, you have to go to very far, right? But within the sequence yn, with the sequence yn, you have to go not too far, right? So this is the idea of the rate convergence. Any questions? All right, so now let us start with the definition of uniform convergence. So now we will come back to the definition of uniform convergence. All right, so suppose we have a series of functions. The sum of fn of x. Right? And we suppose that this series converge to fx in the domain of convergence D. Right? So this convergence means that for every epsilon positive, right, there is this. So this kind of epsilon delta argument, you have to get used to that. There is this n, right? Depending on epsilon, right? So this says that n depends on epsilon, right? The notation n equals n epsilon means that n depends on epsilon, right? So that if small n is bigger than capital N, then the sequence of partial sums, right? So the sequence of partial sums right, minus fx is less than epsilon, right? So this is a quite a complicated definition, right? So So this epsilon is the accuracy that we saw before, right? This capital N is how far you have to go, right? It does not only depend on epsilon. It depends on epsilon, but it also depends on epsilon, and it depends on x as well, right? It depends on both epsilon and x. Right? So so if this capital N depends on both epsilon and x, we say that the sequence converge, right? But this capital N, right? If N, capital N, only depends on epsilon, right? Depends only on epsilon, but not x. We say that the series converge uniformly to fx. Right, this definition is very hard to get at first, right? So I say it again, right? You have a series of functions which converge to a function fx. So this means that for every accuracy epsilon, right? You want to know how far you have to go to the in the series, so that the partial sum is close to fx within the accuracy, right? But this capital N, right, depends on both epsilon and x. When this capital N depends only on epsilon but not x, then you say that the series of functions converge uniformly, right? So this definition is very hard, right? But I want to give an example. Right? I want to give an example. It's a very very intuitive example, right? So I want to give an example. And I will give two examples actually. Right? So the first example is these examples are the examples that we saw before. Right? So we have fn of x is the sequence of constant functions is 1 minus 1 over n. Right? So we saw this example before. Right? So we saw the pictures. Right? We have the green line and the red line. Right? So this is 1. The red line, y equals 1. Right? And the green lines is like this. Right. So f1 of x, f2 of x, f3 of x, and so on. All right, so let us see. Suppose we want this is not an example of a uniform convergence of a series, but you can make the same definition for uniform convergence of a sequence. So I want to tell you this uniform convergence of sequence. So this is about uniform convergence of sequence of functions, right? Not a series of functions. Right? So, all right. So let us start with the accuracy, the precision, epsilon equals 10 to the negative 3, right? So you want that fn of x minus fx is less than the precision 10 to the negative 3, right? So in this case, fn of x is 1 minus 1 over n, right? And fx is 1, right? So you want the precision 10 to the negative 3. So n has to be at least 1000, right? All right. So if you go and you see that this length, capital N, right, is 1000, right? For every x, for all x, right? So suppose you want an accuracy of or a precision of 1000, right? So you want all the graphs to be within the shaded graph, shaded region, the region that are shaded, right? So you have to go as far as f to the f of 1000, right? You have to go as far as f 1000, right? Or f 1001, right? And f 1002 and so on, right? So you see that all of the graphs of f 1001, f 1002, all of these graphs are within the shaded region, right? Within the pink region, right? So this is 1 plus 1 to the negative 3, and this is 1 minus 1 to the negative 3, right? So this is a picture of a uniform convergence, right? So in this case, you have a uniform convergence. You have a uniformly convergent sequence of functions, right? All right, so this is the first picture, and let us come to the second picture, the second example, right? So the second example, right? All right, second example is also the example that we saw before, right? That we saw before. You can guess what this example is, right? So now I will take fn of x is 1 minus 1 over n times x, right? So we saw this this picture before, right? So this is the line y equals x, right? Fx equals x, and you have the green lines. You have the green lines. F1 of x, F2 of x, and so on, right? F2 of x. All right. So now you want to measure the accuracy, right? You want to measure the accuracy. Right? So you want the precision. You want the precision to be 1 over 1000, right? So let us draw the precision here. So you have a parallel line, right? Here, right, and here, right? So you want to be within this precision, right? You want to be within this precision. So this is the function g of x equals 1 minus 1 over 1000. G of x equals x minus 1 over 1000, right? And this is h of x equals x plus 1 over 1000, right? All right, so now you see that for any green function, you see that some part of the green function will be in the shaded region, and some part will be outside of the shaded region, right? So you have a green function, and it will be within the shaded region for some times, but eventually it will be outside of the shaded region, right? So in this case, you no longer have a length, so that all of the functions after that length will be within the shaded region. So now you no longer you have a convergent sequence of functions, right? Right. But this sequence is this sequence does not converge uniformly, right? Because within the shaded region, right? Say for x equals 1000, right? You need to go far enough along the sequence so that it is within the shaded region, right? But if you go further, say x equals 10,000, right? X equals 10,000. You need to go further along the sequence so that it belongs to the shaded region, right? So so this capital N, right, depends on 1000, right? But this capital N is much bigger, right? So you no longer have a uniformly convergence, right? So this is the picture of a uniformly convergent sequence of functions, right? So it is kind of difficult to get at first, but we'll get used to that, right? All right, so I want to mention a criterion which is called Weierstrass.
I have a question.
Yes, please.
Does it mean it is uniform convergence when the rate of convergence doesn't depend on it?
Yes, that's precisely the definition, right? When the rate of convergence doesn't depend on x, then it converges uniformly. That's precisely the definition.
Yeah.
Right. So that's why I gave you two pictures so that you can think in pictures about the uniform convergence, right? And you can think about the uniform convergence in terms of the rate of convergence, right? All right. So when we have a sequence of functions or a series of functions, we want to see whether it converges uniformly, and to say whether a sequence or a series of functions converge uniformly. So sometimes you have to use the definitions. And you can think in pictures, right? And think in pictures and in terms of rate of convergence, right? All right, but there's a criteria which is Covey-Strass criterion. It is not useful all the times, but it is sometimes useful. But there is a useful criterion, right? Useful criterion, but this criterion you cannot use it all the times. It is only a necessary condition. No, sorry. It is only a sufficient condition. Right? It is a sufficient condition. A sufficient condition for uniform convergence. Right? All right. So let us state the theorem. Right. So this is all right. So suppose we have a series of functions, the summation of fn of x. All right. And suppose we can find a sequence of numbers, say t of n, right? Such that first we know that fn of x is bounded in absolute value by t of n, right? And suppose that we know that the series, the sum of t of n converge. Right? So so it means that all right, I'll state the theorem first, and I'll say how you remember it, right? So in this case, you can say that the series of the sum of fn of x converge uniformly, right? So there's one way to think about this, right? Oh, but by the way, this converge uniformly, I'll tell you what it's called in Vietnamese, right? So you have a series of functions, right? And you compare it with not just a sequence of functions, but not just a sequence of numbers, but a series of numbers, right? So actually, the way to think about this is is as follows. So you have a series of functions at n of x, right? And you compare it with this is how you think about it, not you compare it with the series of functions Tn, right? So if fn of x is less than Tn, right, then the sum of fn of x, right, is less than the sum of Tn, right? So this is the first condition, right? So furthermore, if you know moreover that the sum of Tn converge, then the sum of Fn converge uniformly. So you have to find a series, the sum of Tn, right? So that you can compare the sum of Fn with the sum of Tn, and you have to prove that the sum of Tn converge. You need two conditions, right? You need two conditions, right? So let us give an example, very simple example, right? So you want to show that the sequence of sine of the sum of sine of nx over n squared plus x squared, right, converge uniformly. All right. So how do you do that? You use Weierstrass criterion, right? So use Weierstrass criterion, right? So you know that sine of nx over n squared plus x squared, right? In absolute value, it is less than or equal to 1 over n squared plus x squared, right? But the 1 over n squared plus x squared depends on x. You want an expression which doesn't depend on x, right? So this is less than or equal to 1 over n squared. So the first expression depends on x, right? So the second expression does not depend on x, right? So you want a sequence of numbers or a series of numbers, right? So now you can do the comparison, right? So this is the first condition, right? So then you think you compare the series sine of nx over n squared plus x squared with the sum of 1 over n squared, right? But you know that you know that the sum of 1 over n squared converge, right? Because it's a P series, an Euler series, a zeta series, right? So therefore we know that the series of functions converge uniformly. All right, so that's all we have for today for the for uniform convergence. So any question? All right, so